So as we already said this. We talked about, so there's 500 equations for 500 kids with 500 intercepts, 500 slopes. Each child I at school J has their own slope. Everyone's getting their own growth function. And we can start to, as we already said, look at why is it that this child, what are the characteristics why one child may have a small slope and another child may have a much larger slope. And that's the slope now is what we're going to look at, their growth. That's why people talk about this as growth modeling, because we're modeling growth. So now we kind of move on to level 2, our level 2 model. And so here was our level 1 model. And as we talked about earlier, the level 2 in this sort of repeated measures sort of approach is looking at fundamental child characteristics that may explain differences in the growth patterns that we see in kids. Why are some starting off higher or lower than others? And why are some growing more rapidly over time? And we're going to be looking at those parameters. So kind of one natural question that, as we're kind of framing right here, is looking at why does a student's SES, their socioeconomic status, does their SES explain why they start off higher or lower? So I'm asking a very specific question. I'm asking about when they start in the project, does SES explain why some may be higher or lower than others? In this case, we're going to use a variable SES, which we're centering. And this is actually, it's kind of fun. I mean, you see a lot of, well, we're going to center SES, and we'll see kind of why in just a second. So the average, remember back to, we're doing centering with interactions. And with centering, the average for that variable becomes, you subtract the average from every variable, so the average becomes 0. So the average SES, the average income for whatever, the average SES for, a child at the average SES will have a score of 0. That's what I'm trying to say. So a child at the average level of income will have a score of 0 on SESC, and that's important in just a sec. So what we're going to do is we are taking that pi 0j, and notice we're now making it an outcome for a whole new regression equation. This is our level 2 model. And we're using as a predictor of that intercept, that level 1 intercept, as a predictor of what the child's baseline, what the child's original times 0 score was. We're predicting their intercepts, their score at the start of the study, based on their SES is now the predictor. And this is a level 2 model. And we're going to have we'll see, we'll have more than that. But again, notice now what's fundamentally changed is that the regression coefficient in level 1 is becoming our outcome variable in level 2 from a functional sense. And this is what's kind of lost, I think, in the text, trying to get into it too condensed in a way. You kind of lose sight of this, that we're predicting, and then you can see you can plug the math in and kind of avoid writing it out like this. But I like laying the equation out this bluntly, or this detailed. Okay? This is what this is getting at, kind of visually. Here's what we're looking at. Is this sort of thing. It's asking, is this sort of thing going on? But notice we've got high SES kids, low SES kids. Does SES explain those differences in baseline scores? That's what that regression equation is asking. That's what that level 2 model is asking. is there something going on? Does SES explain why we see that difference? So our outcome for level 2, you can think of it, is 500 intercepts. And we're predicting, right, pi 0 ij is the intercept, pi 0, for student I at school J. There's 500, 25 kids at 20 kids at 25 schools. Based on beta, now I know it's beta, but this is an unstandardized coefficient. It's just the notation, because it's the Greek. But it's the unstandardized coefficient. Beta 00j, 00j. This is where the notation, it gets a little crazy, and it's not on the test. Because why is it 00j? Well, we're predicting pi 0, so we're predicting the intercept 0. This is the intercept for the intercept at school J. So we're predicting every child's, right, so, and so beta 00j, what's that going to be? What's that going to be equal to? Well, it's any intercept. We always know that the intercept is the predicted score when it's your predicted outcome when your independent variable is equal to 0. Well, our independent variable here is SES centered. Because it's centered, it's the average SES.
Say that again?
Because it's
predicted outcome
when the independent variables are equal to 0, right? Because if this is equal to 0, then that drops out. And our predicted score is just beta 00j. So beta 00j is the average, is that initial math score when the income for a school is 0, when the average income is 0. So it's what are we predicting? It's the outcome. I know it's cumbersome. So it's the initial math level when the income is 0. Right? Because here's income. If income is 0, what are we predicting? We're predicting kids' intercepts. If income is 0, all that's left is beta 00j. But it's not the predicted baseline. It's specifically that initial baseline for a kid at the average income level. It's their predicted score at the start of the study when income is equal to 0. Right? Pi 0 ij is your intercept, every kid's predicted score at the start of the study. If income is equal to 0, all that's left is, so beta 00j is that predicted initial math score when someone is at the average income for students with the mean SES. Beta 01j is the effect that SES has on those initial scores. Right? So here's the score when SES is 0, and this is how much those initial scores go up or down based on SES. It's a little, if your head's spinning, that's all right. The kind of the key here is to start thinking in terms of kind of what's a level 2 question. Well, level 2 is looking at those student characteristics, predicting their, are they starting higher, you know, are they kind of, is that SES? How's SES related to whether they start off high or grow fast? Again, beta 01J is that effect that SES has on the initial values. So we're going to see, is that different? Is that, are those, is it, what's the effect of SES? Level 2, we can kind of similar. Notice we did one level 1 model, level 2 model based on pi 0 ij. We can do a second level 2 model based on pi 1 ij, which is the slope. So this is that growth. This is, now we can see what's related. So here we looked at, is SES related to the intercept? Now we can look to see, is SES related to the growth? And we're just plugging in that regression coefficient as our outcome for another level 2 model. And again, we can have SES as a predictor. So we saw, did SES predict their initial level? Did SES explain why some kids started above or below the average? I'm sorry, above or below each other? Now we're looking, does SES explain why some kids show more or less growth over time? So growth is now our level 2 outcome. Ooh. I think it's cool. It's beautiful. Visually, this is what we're talking about. So this is, if it helps to kind of think conceptually, what am I asking? It's asking this question. We've got different growth. Does SES explain why one kid's flat and the other kid's not? Does income explain that variability? Okay? So we're now, just like before, we had 500 intercepts. Our outcome is 500 slopes. Beta 10J is that growth rate when SES is 0. And notice, we've still got the, I should have pointed that out earlier. Notice it's beta 10J. So there's still J different beta 10s. Every school. So now we're coming up with a model for each school. There's J, right? 25. So every school is going to have a regression equation predicting the growth rates for kids in that school. Ooh. Yeah, I know, it's kind of...
Well, tell me if I'm wrong. I'm conceptualizing this right now as a bunch of regression models layered on a bunch of regression models within
Yes.
a bunch of regression models.
Yes, that's exactly. Now, mathematically, it does this all kind of in one big fell swoop and plugs this into that and that into that, and you end up with a big messy equation. But if you do it that way, and that's kind of how you do it in SPSS, you lose sight of what this is actually doing. I think certainly from a teaching perspective, and again, this is like halfway through. This is a month into the HLM course, so it's kind of a little crazy to kind of do this. Again, we're just sticking at the conceptual level, and hopefully, if you sit there and think, yeah, this is kind of cool. I'd like to do this. I've got these questions. I'm interested. Does income influence their growth? And in a minute we'll see, do school characteristics influence the effect of income? Are there school characteristics that really help poor kids and school characteristics that really screw over poor kids? This is how you do it.
So are you asking, is this better than just doing, is that how do we
Well,
get
that's
that?
my next question. But
That's
you
how
just-
people used to do it.
you
Yes,
just said
people.
You look a little funny, and I was like, well, this is how I'm conceptualizing. Tell me if I'm right or wrong. But yeah,
No.
my next question is definitely, I thought.
Why can't you just do all those? Why not just do 500 regression equations
Right.
and calculate all those betas and plug them in and do it that way? That's that's how people actually did it for a while. My advisor, when I was in grad school, had me do that one time. As the idea started to come out, and there wasn't really software to do it, so people were writing their own code. And before I could write code, I still couldn't write code that could do this. I'd have to pay someone. But now there's software. So you would see people, as a kind of a fix, they would do exactly that. I'll do my 500 regression equations, and I'll calculate those betas, and I'll do analyses. I'll do 25 regression equations where I take all the kids in each of those 25 schools, and I'll calculate this regression equation using those 25 slopes. I'm sorry, using those 500 slopes. And I'll do 25 regression equations for those. But the problem with that is it's, without getting too far into it, the errors are wrong. Because in a way, once you, remember when we talked about multiple regression? When you add another variable, it's, we talked about, okay, I calculate based on my first independent variable, and you can think of, okay, I get the residuals, and then what happens when I add another variable, what it does to those residuals. And I kind of pointed out, the problem with that analogy was, it sounds like you calculate the first, and you put in one variable, and those affect that regression, those regression coefficients are set in stone. They're kind of, and now you add another variable and it's kind of working off of that, when in fact it redoes the whole analysis with both variables simultaneously. The same thing here. If you do it that way, you're saying, okay, let's first calculate the time effect, and I get a pi 1ij, and it's set in stone. I can't let this number change based on the effect of future variables when it should. It needs to be calculated simultaneously. All of those need to be done in one model so that the errors are minimized across all of the different levels and all of the different models. And appropriately minimized. So, clever solution. My advisor, who asked me to do that, is now president of the University of Washington. So, see, you had the same idea. So, go become president of the university. So, good thinking, but no. That's the problem. But it's good logic, because and I think it helps to think about it that way. That even though we are not literally going to do that, thinking about this sort of layout that helps you with understanding what those coefficients are really telling you. Keep going? Okay. So again, we're